Good morning, this is Dr. Jingbo Louise Liu. Today we start the chapter 10, the shapes of molecules. In this chapter, we are going to discuss three key topics: depicting molecules and ions with Louise structures. The second topic, the Valence-Shell Electron-Pair repulsion theory, is also called VSEPR theory. The last one will be more focusing on the molecular shape and the molecular polarity. We are going to recall the electronegativity, and then you determine the polar bond based on the geometry, and the polar bond we can determine the molecular polarity. So first of all, I'm going to show you several key steps in order to convert a molecule formula into a Louise structure. We already learned Louise electron dot symbol, so that's used for denote the valence electrons in the particular element. So today we are going to discussing the formulas, the molecules. In order to convert a molecular formula such as nitrogen dioxide, boron trifluoride, we need, essentially speaking, 4 different steps to obtain the Louise structure. First of all, you are going to place atoms with lowest electronegativity in the center. The element with the lowest electronegativity will be placed in the center. So this is called atom placement. Followed by step 2, we are going to add the A group numbers to calculate the sum of the valence electrons. The group A series, if you remember, group 1A, 2A, 3A or 13, 4A or 14, all the way to 8A's. Those group number for the A series, for the representative elements, equals to the number of the valence electron. And then based on this total valence electrons, we are going to start step 3. Draw the single bonds if you have 2 electrons shared, and then you subtract 2 electrons for each single bond. And then the 4th step, you are going to, after this, you determine the remaining valence electron. From there, we are going to go for the 4th step. Give each atom 8 electrons. You call arc-tight rule for the elements mainly from the period number 2 and onward. For hydrogen, for helium, sometimes for your lithium, Li, you may consider duet rule, 2 electrons. From there, after this placement of atom, sum of the valence electron, remaining valence electron, you are going to obtain the Louise structure. So let's see the example. For example, we have the formula NF3, nitrogen trifluoride. First of all, you write it down, your molecular formula accurately, and then you determine which one has a lower electronegativity. We knew fluorine has the largest electronegativity. Therefore, the nitrogen will be placed in the center, surrounded by 3 fluorine. This fluorine F, also called surrounding element. This nitrogen is called central element. It's located in the center, called the central element. That's your atomic placement. Yes, you place your different atoms, and then you are going to add the A group number to determine the total number of valence electrons. For your nitrogen, you have 1 nitrogen which is in the group 5A. 1 times 5 equals 5 valence electrons for nitrogen. Fluorine, you totally have 3 fluorines, and then each of the fluorine you have 7 valence electrons. 7 times 3 plus 5, totally 26 valence electrons. And then you are going to draw a single bond between nitrogen and fluorine. So nitrogen, fluorine, nitrogen second fluorine, nitrogen third fluorine. You place 3, single bond. And then you subtract 6 electrons from 20. So you have 20 more electrons remained. Those 20 more electrons, we call them lone pairs. 20 electrons equivalent to 10 lone pairs. How you are going to distribute these 10 lone pairs? You are going to follow the octet rule. Let's see your nitrogen. Right now, your nitrogen has 3 bonds, 3 single bonds, meaning you have 6 electrons. Therefore, you give your nitrogen 8 electrons. How you are going to do that? Nitrogen needs 2 more electrons. Therefore, these 2 more electrons, they are remained unshared, not bonded. You call this valence electron. So nitrogen has 1 valence pair, have lone pair, and then 3 bonding electrons, totally 8 electrons. Your fluorine, so you have 1 bond, 2 electrons, meaning your fluorine needs 6 more electrons. So you need 3 lone pairs. 3 lone pairs plus 1 bonding pairs, totally 8 electrons. And similarly for the other 2 fluorines, you also put 3 valence electrons. 3 valence electrons for 3 valence electron pairs, lone pairs, and also for 3 fluorines, totally 9 lone pairs. 9 plus 1, 10 lone pairs, up to 20. Double check on the number of electrons. So you obtain the valence electron. Based on the valence electron, you determine the Louise structure for your nitrogen trifluoride. So let's try one more example. So we are going to write the Louise structure for 1 molecule with 1 central atom. Example is difluoromethane, CCl2F2. This is the compound, one of the important compound, which is responsible for the depletion of stratospheric ozone. How we are going to convert this formula, molecular formula, into the Louise structure? Also, you are going to have that, 4 or 5 steps. Step 1, you determine which element has the lower electronegativity. Put it in the center. So your carbon has the lower electronegativity, put it in the center. You have 4 central elements, 2 chlorine, 2 fluorine. Put them symmetrically around your carbon, and then you are going to determine the total number of valence electrons. Carbon, you have 4 valence electrons, 2 fluorine, so each of them is 7, 14. 2 chlorines, each of the chlorine 7, 2 chlorines also 14. 14, 14, 28, 28 plus 4, 32 valence electrons. And then you are going to place single bond between carbon and the 4 surrounding atoms. So carbon with fluorine, carbon with another fluorine, carbon with chlorine, carbon with the last chlorine. So therefore you have 4 single bonds for carbon. Carbon fulfill the octet rule. Your carbon has 8 electrons. We mean valence electrons. And then totally you use 32 minus 8. You have 24 electrons are remained. These 24 electrons refers to 12 lone pairs. You have 4 central element, 4 surrounding elements. Sorry for that. 4 surrounding elements. 12 valence electrons. Each element will have 3 lone pairs. Fluorine 3 lone pairs plus 1 bond. totally 8 electrons. Similarly, for chlorine, 3 lone pairs plus 1 single bond, totally 8 valence electrons. All of the elements fulfill the 4-octet structure. So that's how you are going to again convert your molecular formula into a Louise structure. Some students also just between carbon and fluorine, you put 2 electrons. That one is also acceptable, but I prefer using this single lines. The second important point or terminology is called resonance structures. For example, if you have O3, so we are going to write it down the Louise structure. So make sure every element follow the octet rule. So my suggestion is central element oxygen, 2 surrounding element oxygens 2, and then you put a single bond, and then you make it to 80 electrons. What do we figure out? If you just put the single bonds, and you are not going to make sure everything has 80 electrons, therefore you are going to use a double bond. Use a double bond between oxygen and another oxygen. And then this central oxygen, you have 3 different bonds, 1 double, 1 single, 3 bonds. You need 2 more electrons to make this central oxygen 80 electrons. Therefore, you have 1 lone pair. And then for the oxygen on the very left, let me call it oxygen A. This A, you have a double bond. You need 4 more electrons. In other words, you need 2 lone pairs. Also, the single bonded oxygen, let me call it oxygen C. Oxygen A, B, C. You have 1 single bond, you can have 3 lone pairs. So this is structure 1. Similarly, your oxygen B and oxygen C, they can form double bonds. So you have a different structure number 1 and number 2. Both structures are acceptable. Those structures, they are called resonance structures. The resonance structures is defined as the Louise structure. Both are different and reasonable, but they are used for the same molecule. Point 1, you must be discussing for the same molecules. If you have different molecules, they are not existing resonance structure. Resonance structures are the different reasonable Louise structure for the same molecule. They have different electron arrangements. Neither structure, however, this 1 or 2, truly accurately depicts the O3 ozone. The reason is, in the reality, when we measured the oxygen-oxygen bonding, they have the same identical bond lengths, identical bond energy, meaning if you have double bonds, that bond is strong and shorter. Single bond is supposed to be longer and weaker. However, in the reality, the oxygen-oxygen bonds were measured and the values for the bond lengths and bond energy are the same. So therefore, we use another structure to denote it. We call the resonance hybrid. I will show you in the next slide. Again, these 2 structures has been commonly used to depict the resonance structure for your O3 using your Louise structure. Resonance structures are the Louise structure. Both acceptable for this case, both reasonable, but they have different electron arrangement. So again, your resonance structure have the same relative replacement of the atoms, oxygen A, B, C. The atom placement, they are relatively the same, identical, but different locations of bonding and lone pair, different arrangement of your electron pairs, lone pair or bonding electrons. So again, both structure are acceptable. In between, you use a double-headed two-headed resonance arrow to represent two resonance structures. This two-headed resonance arrow is placed between structure 1 and structure 2. That's essentially about the resonance structure. As we just mentioned, both structures as O3, which can be depicted by more than one valid Louise structure. So in that case, you have another terminology called resonance hybrid. For example, for our O3, previously we're talking about structure 1, structure 2, and we mentioned either structure 1 or structure 2 represents your O3 structure accurately. So which one more accurately represents the structure is this called resonance hybrid. We are going to learn something called electron delocalization. Your resonance forms are not real bonding depictions. Although O3 does not change back and forth between its two resonance forms, the real structure of a resonance hybrid, is the average of its contributing resonance forms. Previously, you remember you have two resonance forms. In this resonance hybrid is considered the average of both contributing resonance forms. In this structure, what you see solid line. Also, you see the dashed line or dotted line. Louise structure depicts electrons as localized. If you remember the previous one, structure 1 and 2, you have double bond, single bond, they're both solid. Solid bond represent localized electrons. Your Louise structures depict the electrons as localized, either on an individual atoms, such as lone pairs, or in a bonded atoms, such as shared pairs. In this oxygen, these two dots represent lone pair. This solid line represents shared electrons bonded between each other. In your resonance hybrid, your electrons are no longer belonging to one atom. They are called delocalized. The delocalization refers to the electron density is spread over a few adjacent atoms, such as oxygen A, oxygen B, oxygen C. They are the valence electrons, that electron pairs. If you recall, if you have double bond, you have lone pair, that two electrons is going to be spread among oxygen A, B, and C. You put a dashed line along A, B, and C. So your electron density is spreading over a few adjacent atoms. You use dotted or dashed lines to show the delocalized electron. Delocalized electron refers to the electrons which are shared by the adjacent atoms. While your elements doing this, try to decrease the electron localization. Spread out the electrons to make the electron density evenly distributed. There is one more important job for us to do, is to write the resonance structures. We are going to use one example, nitrate, NO3 negative. You have a nitrate. In this case, you don't have a neutral molecule. You have a negatively charged ion, anion. And then I want to see the bond order for the different bonds. What's our plan? Our plan will be, point 1, write your Louise structure first. Remember, whenever you have negative charge, you need to add one electron to the valence electrons. Valence electrons need to add 1 electron for negative charge. If you have 2 negative, you add 2 electrons. At positive charge, you remove 1 electron, subtract 1 electron. And then we are going to apply that 5 steps, such as you are going to place your atoms, you are going to calculate the total number of valence electrons, you are going to draw the single lines, and then to determine the remaining electrons, and you are going to apply octet rules to make sure all the atoms follow the octet rule to have 8 electrons. So here is what we are going to do. You place your nitrogen in the middle, in the center, 3 oxygen symmetrically surrounding the nitrogen. And then you calculate the valence electrons totally. Nitrogen, 5 electrons, you only have 1 nitrogen. Oxygen, 6 valence electrons, you have 3 of them. And you do have 1 negative charge plus 1 negative. Totally have 24 valence electrons. Step 3, so add single bond between oxygen and the nitrogens. So you have 3 single bonds, and then you remove 6 electrons. I have 18 electrons removed. Question is, how do you distribute these 18 electrons or 9 lone pairs? I can place oxygen. Each of them has 3 lone pairs. So your nitrogen will have only 6 electrons. If nitrogen has 6 electrons, this nitrogen is not following the octet rule. Therefore, you may consider oxygen and nitrogen to form a double bond. Between nitrogen and oxygen form a double bond, this lone pair will be removed. Oxygen, nitrogen form a double bond. One of the lone pair removed. So in this case, this oxygen, 8 electrons. This nitrogen, 1, 2, 3, 4, 1 double bond, 2 single bonds, 4 bonds, 8 electrons. Let's see, nitrogen and this oxygen, single bonded oxygen, 1 bond, 3 lone pairs, 8 electrons. Similarly, 1 bond, 3 lone pairs for this oxygen, also 8. And then you can write it down, the other 2 possibilities. Nitrogen and your right-hand electron can form double bond. Nitrogen and your left-hand oxygen, this oxygen. Nitrogen and oxygen, you form double bonds. In this case, you have 3 Louise structures. They are called resonance structures. Put these structures in the squared bracket and label it as negative. Again, don't forget this negative sign. Put it in the squared bracket. In between different structures, you place the 2-headed resonance structure arrow, 2-headed arrow to represent resonance structure. In these resonance structures, what we also found, there is something called formal charge. Formal charge is the actual charge that the atom would have if all electrons were shared equally. Again, formal charge is the charge that an atom would have if all electrons were shared equally. Formal charge of your atom can be calculated by this equation. Formal charge equals to the number of valence electrons minus parentheses the unshared electron number plus half of the shared electrons, close parentheses. You calculate the unshared electrons or lone pairs. You count the bonds, and then from there you can calculate the formal charge. For example, our oxygen. For your oxygen A, in this structure 1, you have O2, O3, you have structure 1, structure 2. For my oxygen A, in the resonance form A1, your oxygen A has the formal charge, which can be calculated by number 6, oxygen valence electron for oxygen 6, minus the unshared electron which is a 1, 2, 3, 4. Paired electrons 1, 2, 3, 4, and you going to divide it by 2. So 4 plus 4 divided by 2, 4 plus 4, 4 plus 2 minus 6, and there's 0. Your formal charge for all the different atoms, so such as atom A, B, C, oxygen atom A, B, C, so you can calculate it in this way. In structure 1, structure 2, similarly. I see oxygen B. You have 6 valence electrons. You have 2 electrons which are not shared, minus half of, you have 1, 2, 3, 4, 5, 6. 6 electrons are shared. This half of the electron shared also equals to the number of bonds. Similarly, for your oxygen C, you have valence electron 6. You have the electron which are not shared, 1, 2, 3, 4, 5, 6. That's your valence electrons. And that's your, lone pairs. 2 times your lone pairs minus 1 bond. So you have 0, -1, +1, -1. Totally, this ozone has the charge 0. On the other hand, you can calculate A, B, C in the structure B. And that's how you are going to determine the formal charges. And why you need to do this to determine these formal charges. How do you know which structure is more reasonable? Choosing the more important resonance forms based on the following steps. Number 1, you wish the smaller formal charges to the targeted compounds or ions. Smaller formal charges, either for positive or negative, are preferable to the larger ones. If you have 0, that's the better one. You have +1, +2, your element prefers to the +1. If you have -1, -2, your structures prefers to the -1. On the second point, the same non-zero formal charges on the adjacent atoms are not preferred. If you have adjacent atoms, one of them is positive, another one should be negative. Avoid like charges on the adjacent atoms. If you have 2 atoms, they are neighboring to each other. You wish to give one negative, another one positive. Third point, a more negative formal charge should reside on the more electronegative atom, such as if you have fluorine and carbon, your fluorine should have more negative formal charge. Your carbon should have more positive formal charge. That's essentially about the formal charges. And also I listed several examples, which is called exceptions to the octet rule. If you have larger atoms in the period 3 and onward, such as phosphorus, such as sulfur, they may follow the non-octet rule. So in this case, so you are going to consider the d orbitals. Those ones is not required, it's for your own comprehensive study. And I do show the several examples for the octet rule exemptions. So again, so those solutions is listed for our students to further study. Next class, we are going to learn the Valence-Shell Electron-Pair repulsion theory. It's called VSEPR theory. So in this VSEPR series, we need to know 3 key points. Point 1, each group of valence electrons around a central atom is located as far away from each other as possible to minimize the repulsions. Point 2, a group of electrons is any number of electrons that can occupies a localized region around the atom. Can be single bond, can be double bond, can be triple bond, can be lone pair, can be single electrons. They all considered group of electrons. The point 3, based on this VSEPR theory, we generally classify our molecules into 5 matrix structures. The first one is called linear structure. Second one, trigonal planar structure. Third one, tetrahedral structure. Fifth one, trigonal bipyramidal structure. The last one called octahedral structures. Next class, we are going to discussing these 5 different structures and associated derived structures. So we are going to discussing electron group arrangement versus your molecular shape. We need to know the electron group arrangement is defined by the both bonding and the non-bonding electron groups. Bonding and non-bonding electron groups, they both considered electron group arrangement. The molecular shape is the 3-dimensional arrangements of the nuclei joined by the bonding groups. The molecular shape is defined only by the relative positions of the nucleus, not consider electrons. Your molecular shape is classified using the following designation: A, X, M, E, N. Capital A represents the central atom. Capital X represents the surrounding element, surrounding atoms. Capital E represents the non-bonding valence electron group, that lone pairs, non-bonding valence electron groups. Smaller m represent the number of the surrounding atoms. Smaller n represent the number of lone pairs. N and m are the integers. They are the positive integers. Next class, we are going to discuss the molecular shape and the electron group arrangement, and then we be discussing molecular polarity. That's all for today. You have a beautiful day. Thank you so very much.